Okay, this is going to be a fairly brief video. This is just the beginning notes on the idea of the dot product. Okay, so we're going to define this. We're going to have a vector A, and I'm going to define it in R3, but it could go to R anything finite. So vector A is 1, 2, 3. A vector B being B1, B2, B3, and both of these, according to our definition, are in R3. And I'm going to create a new vector in R3, or a new scalar actually, that we're going to call it A dot B, and this is going to be the linear combination of these two things. So it's going to be A1B1 plus A2B2 plus A3B3. So that's going to come out as a scalar, right? So if this is the case, then we call A dot B the dot product of A and B. Now this is going to have some geometric implications later on, but for right now it's the tool that we're going to use, and we're going to look at some of its properties. Okay, again, the properties here is going to be a brief list, so we're going to make a list of properties of the dot product. And like I said, it's going to be a fairly brief list. It's only going to have 5 items. The first one makes a connection between the dot product, so if I dot a vector with itself, and the magnitude. Okay, so we actually get that a vector dotted with itself is the same as the square of its magnitude. Okay, you could sink into that a little bit, but it's not too hard to prove. Number 2, one of the nice things about the dot product, it's not true of all forms of multiplication, is that you get a commutative property. Again, not too difficult to prove, but it's there. We're going to see some forms of vector-vector multiplication that are not commutative. And when things are commutative, we say that it is an abelian group. So vectors under the dot products form an abelian group. This is good. A dot B plus C. Okay, so we're getting into a distribution here. This is going to be the same as A dot B plus A dot C. So this is a distributive property. All right. Number 4, we're going to say if I take C times A, then dot that with B, and then I'm going to look at C times A dot B, and I'm going to take that as A dot CB. Okay, so this is an associative property. It doesn't matter which vector you apply the C to. Sorry, C, C, C. You can either apply it to A, you can apply it to B, or you can apply it to the dot product. You're still going to get the same value. Now note, you don't get to apply it to both, because then you're going to get a C squared, and that's going to be a problem. So you can either apply it to the A, you can apply it to the B, or you can apply it to the product. Okay, finally, number 5, if I take the 0 vector and dot it with another vector, I get back 0. Okay, so this is the 0 vector, this is a 0 scalar. 0 vector times another vector with a dot product gets me 0. Okay, so this is going to get me what we call a 0 property. And the 0 functions just like the 0 would in multiplication, except for there's a slight difference here that I've got a vector going to a scalar. Alright, so just a quick summary. The dot product takes all of the components of the first vector, multiplies them component-wise by each of the components of the second vector, and gets me a sum. And then that will ultimately lead to a scalar. And then we have this 5 properties of the dot product. We've got this connection between the dot product and the magnitude of the vector. We have a commutative property, we have a distributive property, we have an associative property, and we have a zero property. All right.